And that classification that we've chosen is the dip isogen. And we had some questions on the cards about dip isogen classification, what a dip isogen actually is. And so let's look at that again, make sure we understand. When we're doing a type of dip isogen classification scheme on a fold system, what we're doing is we are looking at both the inner and the outer arc of our system. So this would be our inner arc, this would be our outer arc, and we're setting up a coordinate system. This would be the fold hinge. In that system, this would be the hinge normal plane here. So if I elect, I can choose a, let's say, a 10-degree dip angle. And so I would come in, choose a, this would be my 10-degree dip angle, and I would note that it becomes tangent to the outer arc right there. Then I would take that same 10-degree dip angle, bring it down here, note that it becomes tangent right there. Then those are my 2 points of tangency for that 10-degree dip angle. Then I can connect that. This becomes my dip isogen. That is my 10-degree dip isogen. If I wanted to, I could repeat for a 20-degree angle. There's my point there. That would be my 20-degree dip isogen. And so I would repeat that for all possible dip angles, usually at a 5-degree increment or a 10-degree increment, to fill out the pattern of what my dip isogens might look like. And so in this case, the dip isogens are converging downward. And so what Huddleston did, and this goes all the way back to 1973, what Huddleston did was he traveled around the world, measured all the folds that he could possibly find, and tried to use this classification scheme to see if that fit the range of folds that he saw. And it worked out very, very nicely. So we had, in terms of the dip isogen classification scheme, we saw 3 major groupings. Type 1 folds where the dip isogens converged downward. Type 2 where the fold dip isogens were parallel to each other. And then type 3 where the dip isogens converged upward or they diverged downward. And so Huddleston further described those systems as being, in this case, we would see that the curvature of the inner arc is a little bit greater than the curvature of the outer arc. In the type 2, the curvature of the inner arc was equal to the curvature of the outer arc. In type 3, we determined that the curvature of the outer arc was greater than the curvature of the inner arc. And so we ended up with some fold shapes, and this will be sort of a dramatization. This would be a type 1, where the curvature is far, far greater here than it is there. This would be a type 2, where we have these two being roughly the same. And for a type 3, what we see is something quite the opposite of this. So that this would be a type 3 curvature set. The curvature of the outer arc here is far greater than the curvature of the inner arc. And this is the fold classification scheme that we look at. This helps us begin to understand how do folds actually form. Because one of the challenges, one of the many, many problems that we've had is that we know that we find folds everywhere. Anywhere we go, any tectonic regime that we're in, we're going to be able to find folds. If you are a seasoned field geologist, you get into a field area, it's not going to take you very long to find folds in that setting. When we look at these, we know they form in all materials, and I brought some other examples of materials. This particular sample I'm not going to pass around because it's just about to fall apart. This particular sample is a beautiful example of folds. We have what appears to be an antiform here, a synform in here. This is in a blue schist grade metamorphic rock. This was collected in Virginia. This is part of the Brevard zone in Virginia in the Appalachian system. And this is actually the shear zone at the root of the Appalachian thrust belt. Remember, we drew a line down, put a question mark. Well, this is the question. This is that root zone that is the shear boundary between North America and Africa at the time of collision, Pennsylvanian, during the Alleghenian event, where we formed the main thrusting in the Appalachian system. And we have these beautiful sheath folds in here. We have, so high-grade metamorphics. Here we have a series of folds that we're going to call tigmatic or elasticas in this case, and these are in enigmatite. This is in a high-grade metamorphic where we're transitioning from schist into gneiss, and we're seeing injection of melts into the system, then those are getting folded. So that is a enigmatite that has folds. Then we have a couple of gneissic materials. This one is from the Rocky Mountain National Park area, not from the park itself. This particular lovely little fold is one of the folds in that XB formation, the Paleoproterozoic gneiss. And so we have a lovely little fold in a gneissic system. And this one, who are you? Okay, yeah, I remember the conversation. This fold is from the this is from the Bighorn Uplift on Highway 14A between Douglas and Loveland. Yeah.
Okay, you said that one was magmatic?
Migmatite.
Migmatite.
That one is a metamorphic migmatite, where we have an injection of a thin vein of melt through a metamorphic that then gets buckled, and it can form what we call an elastica or a tigmatic type of system. And they can become really quite ornate. I have a beautiful tigmite at home. The only problem is it's too big for me to pick up anymore. I need someone large and strong to pick it up because I can't do it anymore. So it doesn't come into class. So we have folds in all different sizes, all different types of materials, and we began trying to understand how do they interact with surface. How can we begin, as field geologists, how can we begin to recognize folds? Now, on, what's today? Today's Friday. On Wednesday, I gave you a gift. I gave you a fold. Who brought their folds with them? If you need a fold, I made more. Again, spare no expense, remember. Probably the most valuable gift you will ever receive.
I'll keep one more person or two to take out your dates.
Yes, take it. Yeah, take it on your date. If it's not going well, you lose. You know, the conversation drags. This is the perfect way to pick up the conversation. So, if we look at this, we had a hinge in our fold. We can make this an anticline. We can make it a syncline. So this is a multi-purpose fold. So that if we take this fold, remember the orientations that we went through. We have a fold like this, where the hinge line is horizontal, and you can look at it and go, yeah, that's horizontal, and the hinge surface is vertical. We call that upright horizontal fold. If we want, we can have that plunge where our hinge line is now. Do you need a fold, Rachel? Okay. Where? Oh. And you need a fold.
You said the hinge
Who
line?
else needs one? No. Because we all want to do this,
You said the
because
hinge,
now we're going to have a chart.
you said the hinge line was,
Hinge line is horizontal,
and the other was what was
the
vertical?
hinge surface is vertical. Now, if we take this, let's leave the hinge surface vertical and just rotate down. In this case, we have a plunging fold, and it happens to be a plunging anticline. Right? The way we've done this. So this we're going to call, oddly enough, plunging. Now, we can make this be a vertical fold by simply making the hinge line vertical. Tim.
I'm sorry, I'm confused. So this is the hinge surface here?
The hinge surface, good. The hinge surface, Tim, would be this plane that would contain, imagine if we had multiple layers. The hinge surface would be that plane that contains all of the hinge lines
Okay.
through that multi-layer system. And so if we have, where's one of our nicest samples? Where's the nice ones? The big nice ones. So in this case, that would be the hinge surface. Okay, so the hinge surface would be right there.
Contains all the hinge lines.
Yes, because it contains all possible hinge lines. So in that case, we have here, this is a vertical fold. The hinge line is vertical, the hinge surface is vertical. So we have now three different members: upright, horizontal, plunging, vertical. We can come back to here, and now let's tilt our hinge surface. Let's allow the hinge surface to dip. Hinge line still horizontal, but the hinge surface is inclined now. And oddly enough, we're going to call that an inclined fold. Geologists aren't terribly imaginative. So here we have an inclined fold, hinge line horizontal, hinge surface dipping. Doesn't matter if it's dipping that way or that way, it's still inclined. If we take it all the way over, this becomes a recumbent fold. Hinge line is horizontal, hinge surface is horizontal. Okay, so now we've added two more. So let's run through them. Upright, horizontal, plunging, vertical, inclined, recumbent. So
And you said the recumbent was both the hinge line and
both
surface
are horizontal. Now let's come back here, go to our incline, and then have it plunge as well. That's an inclined plunging, oddly enough. So we have now 6 different potential orientations. Now let's go back to our vertical fold, and let's rotate this around a horizontal line. We're going to call this a reclined fold. Reclined? Sure. So it would be a reclined fold, and in a reclined fold, this one, we have hinge line is plunging, right? The hinge surface is dipping. So tell me, what's the difference between this inclined plunging, where the hinge line is plunging and the hinge surface is dipping, and this, where the hinge line is plunging and the hinge surface is dipping? So there's your pop quiz.
Yes. One's closer to the horizontal.
Inclined and reclined.
Inclined plunging versus reclined. So talk to your neighbor, come up with an answer.
I have a question on the incline plunging. Does it have the same as far as the plunge line?
Reclined or reclined?
Hinge line.
Reclined when you كده.
The hinge line and the hinge surface, are they the
Reclined
same as
when
the inclined line?
you كده.
You have our definition.
That's
We
what
have incline plunging, hinge line is plunging, hinge surface is dipping.
Okay.
Reclined, hinge line is plunging, hinge surface is dipping. But there's a difference. So work it out with your associates.
So this,
Do we have an answer?
I think it's closer to where.
As a hint, you use the term in baseball. You use the term, I believe, when you're playing soccer. Pitch. And if you're trying to con someone.
أنا أقول إيش؟ شو اسمه؟ كل واحدة منها one different direction. لازم هذا هذا الانكلاين. الانكلاين بيكون كذا.
So, who wants to explain it? Who's brave? Do we have anyone brave today? Who wants to explain the difference? Ali.
Maybe they will have like different direction on the surface.
Different amounts of pitch? Because remember, what is pitch? How do we define pitch? We defined pitch as the angle of a line within a plane. And so if we take our reclined here, if we reconstruct this, this is our hinge surface here. That's our hinge line there. So if I look at that, and if I look at it carefully, and since I'm an old geezer, I have to look over my glasses to do that. What's that pitch? What's that angle?
Between the surface plane and the line?
Between the hinge surface and the hinge line.
180 degrees.
85.
Hopefully not 180.
90.
Why 90? 45 here, all sorts of angles. Why 90? To the strike. Yes. The plunge of the hinge line is down dip of the hinge surface.
For which one?
That's the recline. So in this case, my pitch is 90. Does everybody see that? You know, really examine your reclined fold, because that pitch is 90 degrees every single time, no matter how you do it, because you're rotating around a horizontal axis, which happens to be the strike line of the hinge surface. So the hinge line will always maintain a 90-degree pitch. Now, let's do an inclined plunging. Is it 90 degrees? No, it's oblique. Start up here, let's go inclined. Now, plunging. That pitch of the hinge line in the hinge surface, that angle is less than 90. It's going to always be less than 90. no matter what your plunge is, because you're not rotating around this horizontal line, you're not rotating around your strike line. Yeah.
I really don't see that. I don't understand how we'd ever have the difference between, the hinge surface will always contain all of the different hinges
The hinge surface, maybe it would help if we do it this is kind of a small sample to do this on, Tim. In this case, this is upright horizontal. If we were to come over and make this system a vertical, now I'm going to say, here's the strike line of my hinge surface, right? If I rotate around that, this is my hinge line. My hinge line always stays perpendicular. Now, if I take this, now keep this 3D in mind, and if we come back to this one, we're going to start off upright horizontal, we're going to incline it, now we're going to plunge it. So that in this case, the strike of my hinge surface is going to be along this angle. This is the strike of my hinge surface. My pitch is that angle there. I guess I can do a Vulcan salute. There is my pitch, and it's less than 90. Okay?
How do you know the strike is that direction?
Well, let's take a look at this. Let's take a look at this hinge surface. We come in here, and that's my hinge surface.
Yep. Yep.
So this is plunging. So my pitch angle's this angle right there.
Gotcha.
And so that's going to be less than 90. That's going to be an oblique angle. So we have 7 different orientations. So let's run through them again. Upright, horizontal, plunging, vertical, reclined, inclined, vertical, inclined, recumbent, and then inclined plunging. Now let's add one level of complexity since this is child's play, right? Yes.
Can you define pitch again?
Pitch is the angle between the strike line and a linear feature within the plane, measured always within the plane. So, 7 different orientations: upright horizontal, plunging, vertical, reclined. Inclined plunging, recumbent, and just plain inclined. So inclined, inclined plunging, recumbent. Right? We're good? And we know from physical geology, we know some of the basic rules of anticlines. If we have a true anticline, the layers will dip away from the hinge line, right? So that if we have a true anticline, the layers will do this. And this will be oldest in the hinge zone, getting younger away. We're good there? So that's our definition of an anticline. Where the hinge contains the older materials, the core of the fold, the layers dip away. So that if we look at a map pattern, and we have a map pattern that looks like this, where let's say we have 2, 3, 3, this would be 4, 4, then that is my anticline. Okay? A syncline is just the opposite. A syncline in this particular system is going to have the younger materials in the hinge zone of the fold. So this would be 1, 2, 3, and the layers will dip in toward the core of the fold. So if I had a map like this, where in this case, younger materials, 3, 2, 1, 1, this would be the hinge of my syncline. My layers dip in towards the center. In this case, the layers dip away from the center. Okay? Now, we used the simple mnemonic of a block diagram. And we want to start thinking about our fold, our friend here. How is it going to interact with a topographic surface? How is it going to interact with a cross-section? And we're going to have the cross-section be either north-south or east-west. And the device that we use is a simple block. So on your challenge, I've given you a series of empty blocks. Oh, you didn't get the challenge? So you have to make it up. So we worked a couple of simple examples where this would be our block diagram here. We're going to come back and then out like so. In our block, this face right here, we can visualize this as an east-west face, okay? So this is an east-west face of a cross-section. So we've taken the Earth and we've sliced it along an east-west line. This would be a north-south face. And again, we've taken a face and cut the Earth along a north-south line. And then this is our map surface, so that we have a block. And what happened to our blocks? Okay, they've vanished to disappear. So we have a block of the Earth here. And we want to fill in a fold. Now, we drew a very simple one last time, where we had something that looks like this. Let's say that it is horizontal. This would go back like so. And then I'm going to ask you, is that an anticline or a syncline?
Anticline. Looks
like an anticline. We would want to verify that this is truly an anticline, and then age date. This is oldest, 3, 4, 5. So on our map, we would have 5, 4, 5. Here, 5, 4, 3. We would put in a different color. This is our hinge line, and it should be shown with the layers dipping away, an anticline. We can also adorn with a strike and a dip, like so. On our map surface, you only put these these sorts of symbols on the map surface itself. Because geologists, much to our chagrin sometimes, we can't walk through the body of the Earth. That would be very cool to be able to do that, to be able to see what's going on in the subsurface. So here we have an anticline. What kind of anticline is it of our 7 end members? Yeah, upright horizontal. This is an upright horizontal anticline. And we did an upright horizontal syncline, right? Last time. Now, let's add one level of complexity. And Angelina, I said I was going to pick on you. Yes. So, here we have an upright. Let's make it plunge. What would that block diagram look like? So, I'll draw the block, I'll do the hard part. Let's make this one be our orientation. Let's set this up for her. So the hinge is going to have a strike of north, 0 degrees east, and it is going to be vertical. The hinge line is going to plunge 30 degrees towards the north. Okay, so, Angelina, thank you for volunteering.
I didn't volunteer.
Oh, I thought you did. So, what is it going to look like? Help her out.
I mean,
Tell her what this should look like.
so we know the hinge line's gonna be coming like, basically, from
Okay.
or straight through here.
So we would have it here and then probably go off that way since this is north.
Yeah, exactly. But
What would it look like down here?
I guess.
Well, it's an anticline.
Yeah. So I guess it would be kind of, I mean, this is gonna be down here, like the top's gonna be down here, so we're gonna have something, I mean, I know how we're gonna, I'm assuming it's gonna be more.
Well, let's
angled like
think about this because what we want, and guys, you can help her out by taking your fold and doing the same thing. Here's what it is.
Yeah.
So down here we see exactly the same stuff as right there. Right?
I thought it was, wait,
It's an anticline.
I thought it was vertical. Oh my God.
The hinge surface is vertical,
Oh.
but it's plunging 30 degrees to the north. So then we would still see this.
Yeah, but then would it be more like?
Yes, it
This
would
was
go
gonna
down
be this
that way.
yeah.
And then the question is what happens up there?
Yeah, when
Tim.
you,
Sorry, I have a big question. I guess I'm still not understanding the hinge surface. You said it was a plane containing all of the hinges?
Uh-huh.
So how does it have a different orientation
The
than
strike.
the hinge line?
Of the hinge surface.
Okay.
If I have my hinge surface here, my strike is defined as the horizontal line in that. And in this case, my strike is north-south. My dip of the hinge line is still vertical. So this is the strike and dip of the hinge line. This would be the plunge of the hinge line itself. Strike and dip of the hinge surface, plunge of the hinge line. Does that,
Yeah, it does. Thank you.
okay, so let's just connect these up. Let's
yeah.
put that one in, put that one in. Oh, perfect. And that one's gonna have to go intersect right there.
It is an intersection?
Oh, yeah. And it's gonna come down. So what's gonna happen up here?
Yeah, would you even, are you gonna have like an output from the top like that, or are you gonna have,
Let's look at it.
since it's doing that way?
If I cut that with a horizontal plane,
So you're only gonna have.
I see a nose.
Yeah.
So let's put a layer over here and have it on the ground.
I like that.
Okay. Yeah, we got a little bit off, but let's have it come right in there.
This way?
Yeah, perfect. So we have a case where, take your paper, your fold, I mean, sorry, that's the meaning of the paper.
So you're gonna keep seeing like the fold?
Yeah, you'll
This
see
way
that.
like this instead of having.
Yes, instead of straight lines, it's gonna curve. And then that one would plunge off, exactly. So in this case, I have this, if you cut this with a horizontal plane, the arc you would form would point in the down plunge direction. Okay? Do we see that?
Yes.
So that we have a block, thank you. We have a block diagram of a plunging anticline. Do we see that? It would look like this on the east-west face. On our north-south face, since it was plunging to the north, they would go down to the north in that exact angle, exactly as Angelina has drawn. And up here, it would form a curve, a nose. Because we cut that with a horizontal surface. Do you see that? Okay, who wants to dare take on a syncline? Okay.
So if it's, the hinge is vertical, which
The
I
hinge
thought-
surface is vertical. I should say this is strike and dip. Surface.
Oh, I see.
So
it's not,
we've taken this and we've just rotated down. Strike and dip of the hinge surface is still vertical.
so it's still like upright.
Yes, but it's plunging. We're allowing the hinge line to plunge. And so that forms temp.
I have a question now. Earlier you're describing the difference between the inclined plunging.
And reclined.
Yes, exactly.
Right.
Or just, I'm sorry, just the inclined, I think, because you said the inclined.
Well, this would be inclined like so.
Oh, okay. So yeah, then it has to be inclined and plunging. So with the inclined and plunging, something like this, that, and then that, the strike would be there.
Yep.
And then this is supposed to be the hinge line, but that angle to me doesn't look like it's 90. So
No, it need not be.
Okay.
Because if I have an inclined plunging
Mhm.
like this, you're exactly right, this is the strike.
Yeah.
This would be the pitch
Yes.
of that, and my plunge would be measured in this orientation,
Okay, so what's the one that's 90 degrees then?
reclined.
Reclined.
So go vertical and rotate around your strike line. There you have
That's 45.
it's 90,
90, excuse me, yes, yeah. Okay, thank you.
all right? So who wants to take on a syncline? If I don't have volunteers, I'll call it a name at random.
I volunteer as tribute.
All right. Okay, so let's draw the block. There you go. And let's do the same thing. So same orientation. Hinge line is plunging 30 degrees to the north, but it's a syncline. What's it gonna look like?
We're gonna have the layers that it's gonna go like this in the front.
Mm-hmm. Perfect.
We're gonna have the dip in this direction down here.
Yep, yep.
But in this case, if it's cut off like that, then it'll kind of,
So it's going to,
Or to be the same, like cut out
Ooh.
before, you're gonna have
You're
the
gonna-
curves on the top.
Arc it, arc that one and close it, close the top one.
Yeah, like arc it, like
No,
continue
no,
the
no,
arc
no.
like I did with the.
Make that one like an oval, close it off.
that would be an incline.
No, yeah, no, like continue the curve up to the block, Mariah,
Just
like
make it
continue
light.
the curve up to the block, like, you're gonna see the same thing, but on the top of it.
We have referees. See, what is that? That's-
No, like curved.
I guess we missed the field goal.
Remember how the, yeah. Since it outcropped like that with this. Right?
Yeah, and then you just have that one come off, have that one go over there. Yeah, and then let's just open this one. Yeah. So the nose would come the other way. Thank you, Laura. Does that make sense?
yeah.
And so one way to work with block diagrams is to always keep your fold with you so that you can begin to visualize what it's going to do with your surface. Now, we have 10 minutes for the beginning of our challenge. This morning when I passed out cards, there was a number on it. Find your corresponding partners and start working on your challenge. Because some of these are simple, some of these are not. Some of these are a wee bit devious.
If you're a 5, come over here.
So you should have 1 through 6, and they were randomized today, shuffled.
If you're a 5, come over here.
Oh, of course. My gosh, I'm so.
Mariah, thank you. And Angelina, thank you.
Five?
Wait, does anyone say right? No. Say 23. Alright, Harley, see you again.
How you doing, sir?
I think you guys are over here.
Alright, Harley, it seemed like you were circumstances, so.
Chair in the end.
I'm a 2.
So my suggestion is before you even put it on here, let's just like go.
Forget your goals.
Yes, yes.
Are we just turning
Really
one?
think, really think about what
Dr. Tapper,
those things, because some of these are gnarly. Some of these are.
doing something similar in my class.
Okay.
Dr.
Some of these are a little bit devious, and so really think about what it might do.
Is everybody in their group turning it in, or just one for the whole group?
One for the whole group, but everybody contributes.
And how many are we doing for today?
As well, we'll get as far as you can. It's due Monday. And so, try to make sure you understand,
Yes.
because you may see these again.
Oh.
This will be on the exam then.
Ominous.
That's a fairly good deduction. So maybe you understand the way the system works. Yes.
Yeah, but that's just like, yeah, that's just.
Yes. So if you have a vertical fold, this is the map surface. This could be the east-west surface.
So let's make sure we see those. So that this would be
So in this case, it's inclined.
like.
So let's do this. Inclined. It is north 90 degrees east, and
So like,
that's east-west. That's always east-west. That's your north arrow. That's always south to
Just
north.
saying the strike is 90.
So in this case, inclined, but its hinge surface is north 90 degrees east. Right? And then it's dipping 45 degrees south. So now you see your fold over here.
So
There's some
we have
straight
the
lines
strike.
there.
That is-
There's some straight lines there. Does that make sense? And so always read this and guess.
Sound, it would refer to, yeah, so for the first.
This is the map.
Yeah, that's right.
Okay, so incline with the hinge surface north 90 degrees east. So we rotate that 90 degrees.
How about you just go to the second
And it
those at least
is
have
45
one.
degrees to south. So if I cut this on the map surface,
Just like this thing, so
yes,
you
you'll
read
see
like,
the fold over
for
here.
this one, it's east 45 degrees south. start with the first layer.
Makes sense?
So that's actually, I'm looking for getting this information when you're saying, block like this.
Yeah, I got it. So,
Yes.
hinge surface is here.
And then it's inclined 45 degrees down.
It's east.
And so on the map surface up here, you have just a straight line over there. Yes, your fold is over here.
So, we have hinge
And
surface
then the
there.
straight lines over there.
So, is this what you mean by like 90 degrees? So is that and then
Just remove the strike.
that way.
Strike is
In this case, if you say like this, north 90 degrees east, so I'm going to start here, that's north south, move this north 90 degrees east, and then I'm going to have it dipping towards the south.
Oh, so like, so then,
So that you imagine when you cut this,
Okay.
you just have
So-
horizontal lines
at the
here.
top, but like,
It folds over here. And it's straight.
Yeah.
Does that make sense?
Yeah, you're saying that's the
So incline plunging syncline. Okay, so I'm getting mean here. So now we make a syncline. And it's north-south, and it dips 70 degrees to the west, and plunging 30 degrees to the south. So it would be over here, and there, and straight line shift.
that way.
so this is 70 degrees west,
So I have it like this. There's that fold.
and then down 30 degrees down.
Down 30 degrees.
Okay, now.
I'm confused as far I'm confused as far as what to use.
Ah,
So we have an incline and a fold, so this is an incline.
Perfect. Now, that's oriented where it is east-west. That's my strike.
Oh, so is this 90 east?
North 90 degrees east. So that is north 90 degrees east. Now let's incline it 45 degrees relative to the block now, 45 degrees to the south. Because that's your north in your map. So if we now did, we cut that, we have straight lines. If we cut this, we have straight lines. If we cut this, we see our fold over here.
Right, okay, so this is.
That's the strike and the dip of the hinge surface.
Okay, so 90 degrees is just the orientation and fold, and 45 degrees is the degrees of inclination.
Yes.
Okay. In this case, we have 0 degrees. so it
That
would
one's
be-
a little bit tougher.
But it's
So we're gonna start off with a syncline here.
Yes.
Let's start off with our
It's
syncline,
gonna dip 70 degrees.
north, south, and we're going to have it dip 70 degrees to the west, and then find 30 degrees to the south. And so you just, what you're doing is you're playing with your degrees of freedom.
Okay, so
Okay, so you're specifying the rotations, your axial rotations. Okay? One for each group, but you need to be able to draw those. You may see those again.
Dr. Tapp, are we turning in one?
One per group, but work together, make sure you understand.
So it is north 90 degrees east.
yeah.
Okay, so.
More or less my concern is just really good.
It should be like.
Yep, and then it's 45 degrees.
From the south.
And then,
Right?
so, first,
Still should be
here's
another.
the first angle.
Well, I do my good one.
Orientation.
No, but your layers are still the same.
Lee, does this make sense?
I hope so. You know that I still
Not
have.
the answer. That's not the answer that I wanted. I wanted that.
And then it'd be.
And like this layer that's next to this one.
So it's gonna be our actual, incline is here, on this one, traveling that way along the surface.